Okay, AP Physics C. We're gonna do a little note video on statics and torque. Gonna try to keep it short, do a couple quick examples to try to help you get through worksheet 2. So torque is a concept about force and rotational motion. So torque is when we apply a force to something at some distance. For instance, if we have a bolt, let's say, right? And I'm going to make another video here in a second. I'll break a bolt for you. I'll put it in my vise and crank it with the torque wrench. See how much torque it takes to break it. Anyhow, let's say you have a bolt. Well, if I put a wrench on it, a socket wrench, let's say, all right, comes down around it, has a handle that comes off of it, and I can turn this bolt by pulling the wrench. I get a lot more force about the rotational axis of the bolt, twisting force, if I apply the force to the wrench farther away from the rotational axis. Now, obviously, I can only apply a fixed amount of force at maximum, so it's really not the force that's getting bigger, but it does make it easier to turn the bolt. It happens slower, but happens, I can actually do it. It happens easier. And that is the idea of torque. It's this turning force about an axis. It's kind of like the turning force about an axis. So let's think about what that means. So a car with a lot of torque, it can really turn with a lot of force. Those brushless motors we used in Engineering 2, Zach used in his plane, Michael has in his drone, I used in my remote control car. They have a ton of torque. Anna crashed into the wall, broke the tire, broke the wheel hub. I mean, barely touching the throttle. The thing's crazy. I don't mean to put that on her. I've broken it 4 times before that, but it was just a funny specific instance. So something that turns with a lot of, we think, power, force, energy, that's something that has a lot of torque. Big motors that turn heavy objects have a lot of torque. Trucks, when you're in that low gear, have a lot of torque, move slowly. They have to use a lot of torque initially. They have to be geared up for torque so that they can get the big mass of that they're carrying moving. So the calculation for torque, we often start off like we do in that simulation, right? That simulation where we have the seesaw or teeter-totter. I've been made fun of for saying teeter-totter before by students. So seesaw, whatever you want to say. This is the pivot point, wherever that fulcrum is located. If I put a force of 10 newtons at a distance of 3 meters from the fulcrum, the torque, T-O-R-Q-U-E, is the force times the radius. All right? The magnitude of the torque. The symbol we use is a tau, kind of like half of a pi. Force is 10 newtons times 3 meters. It is 30 newton meters. We do not call it a joule. In fact, we leave it newton meters. And we say it like that. Sorry, I'm stepping away. I'm grabbing torque wrench. I'm going to show you a little bit later, but I just want to grab it now. This is my old torque wrench I use to tighten precision things on my car. Now, with the focus lock, I'm not sure if you'll be able to see it. No, you can. This scale is newton meters. This scale is foot-pounds. So force times distance, distance times force. So depending on your car, if you have certain bolts, for instance, they need to be torqued to a certain specification. A light amount of torque is like 15 newton meters. It gets stronger. And I'll show you how this works. It's kind of very clever. The socket goes on here, and this rod bends at a known amount. So when I torque, it flexes. The rod, the handle flexes, and you see this deflection of the scale. It's really pretty cool. But anyhow, I'll show you that later with a bolt and see how much torque it takes to break it. Different bolts have different torque settings that are required. So now the trick here is it's not simply the force, it's actually the component of the force perpendicular to the radial axis. This is your radial axis, this axis that comes from the pivot point outwards. It's the component of the applied force perpendicular to that. This I just treated as magnitudes. In fact, there's something called a cross product involved, all right, or a vector product, which I'm not going to get into too much, but I will show it to you. So if we want to do another one that's kind of similar, we have another plank, a fulcrum, right? Let's say this force now is at a, I don't know, let's say that's a 45-degree angle relative to the plank, which would make it a 45 ready to the normal. All right, here's our pivot point. Here's our radial axis towards the center here. So the torque here, now the way we write this is the torque, all right, and torque, believe it or not, is a vector quantity. F cross R. This is not a multiplication symbol, it's a cross product. All right, so R represents the radial vector, the distance from the center, and F represents this vector. Another way to write this is if you want the magnitude of the torque, so we'll drop the vector signs. It's torque, force, times radius, times the sine of theta, where theta is the angle between the two vectors. So if I want the magnitude of the torque, it's force times radius times the sine of theta. Sine of theta is the angle between the two vectors. So basically it's just this 45 right here. It's the angle between the force vector and the radial axis. And what that is giving us is the component of this vector, because it's sine, right? It's giving us the essentially sine theta, that should be the height of this. That's the component of this force vector that is perpendicular to the radial vector. So that's how you go about dealing with angled forces. It's always that perpendicular component. So believe it or not, torque is a vector quantity. And the trick here is, well, what the heck direction does it point? Well, it points along the rotational axis. So if we look at our bolt example, I'm going to try to draw a three-dimensional bolt real quick. I don't know if I can pull that off. All right, so if we look at our bolt, oh, I messed up that side, didn't I? Look at our bolt really quick. All right. All right, not bad, Harmon. We look at our bolt really quick. When we apply that torque to turn it, right? If we're going to turn it this way with our wrench, believe it or not, the torque is located about this axis. So it's a representation, a way to keep track of things. So the net torque from this force, believe it or not, we use something called the right-hand rule. All right, you take your fingers and you put it in the direction that the bolt is being rotated, and your thumb points in the direction of the torque. So we say this thing has a torque about its axis. It points along the axis. You might say it's a counterclockwise torque. Remember, CCW is a positive torque. Clockwise is a negative torque. That's a direction. All right, and that direction is along the rotational axis of the object you're trying to turn. The right-hand rule tells us the direction. Now, that seems kind of strange, but it's not literally moving that way. Well, yeah, this is a mathematical construction to be able to do later on something called linear algebra, vector algebra, to be able to solve these problems. It turns out we can do torques in 3 dimensions all at once using the IJK notation, which, trust me, I will save you. There's a whole mathematical operation here that says, okay, if we have 2 vectors, okay, let's say it was 1 I hat plus 3 j hat plus 4 k hat, our force, I could cross that with a radius of -2 I hat, some random 3-dimensional vectors. And it's really pretty wild. You set up a matrix. I'm kind of going off tangent here, but you know, that's what I do. You set up a matrix and you find the determinant of the matrix, and that gives you the resultant vector, so to speak, the cross product. So I could take some random 3-dimensional vectors, cross them, and get the magnitude of the vector that is perpendicular to them, and then I use the right-hand rule to figure out the direction. This would actually give me the direction in terms of components, which is kind of cool. But anyhow, torque being a vector component, vector quantity, is really, it's construction. So we have negative and positive torques, right? So if we look at the old Planck, when in static equilibrium, EQ equilibrium, torque net is 0. All right, so this is like net force being 0. It's in dynamic equilibrium when net force equals 0. When static equilibrium means also the net torque is 0, right? We'll do some problems like that going forward here. So when in static equilibrium, torque net equals 0. So we have these problems on the front of worksheet 2, like number 1 here, where we have a 5 kilogram mass here, and an unknown kilogram mass here. The 5 kilograms is 2 meters from the rotational axis, and this one is 3 meters from the rotational axis. So if we want this to be in static equilibrium, the net torque equals 0. All right, torque net must equal 0. Well, that means this one's applying a torque this way, counterclockwise. All right, so that's positive mg, so it's a force, which I'm just going to make 50 newtons, times the distance, 2 meters. This torque, right, this is a negative torque being applied. So when we do the right-hand rule, right, this one applies a torque into the board, which would be, we use an X to represent a torque into the board, and then this one applies a torque that's rotating this way out of the board, thumb up, right? We represent that with a dot. If it's like an arrow, right? Like it's like the point of the arrow coming out of the board, or it's the feathers of the arrow going into the board. We want those 2 torques to cancel each other. So that's the idea of the vector notation. Like the directions, they can cancel each other. So for this one, all right, it's an unknown mass, but it's a negative torque because it's trying to rotate it clockwise. So minus unknown newtons times the distance of 3 meters equals 0. So we just solve for the force of gravity now. So bring this over here. We've got 100 Newton meters equals Fg times 3 meters. Fg must be about 33 newtons, or M must be about 3.3 kilograms. All right, so that's how we go about doing those basic problems, and we just kind of go from there. Now, static equilibrium, torque net is 0. It doesn't always need to be 0. If it's not 0, we'll see how to deal with that in the next worksheet. That means we have an angular acceleration. And we'll talk a little bit more about that going forward, how we then go from torque net to F net, A to alpha. You can kind of figure it out, right? Torque net equals, you know, the sum of the F times R's. Anyhow, it's it's kind of interesting. So we'll deal with that later on. F net equals ma. It turns out the torque net ends up being something called I alpha. Alpha equals A over R, right? So we got to figure out how M and I are related, what the heck that I thing is. We'll get to that later on. Right now we're just dealing with torque equals FR sine theta, where theta is the angle between. So F, let's say this is R and this is theta. R being that radial vector. So number 2 has you determine the net torque in each of these. So this is an interesting thing. When the pivot point is at the center of gravity, like in the first one, here's something you may not have considered, right? The force of gravity is pulling on this down. But the torque due to gravity of the force of gravity acting on this plank is 0 because it's Fg, and well, what's the distance between the force of gravity and the rotational axis? It's 0, right? So the R in this case, the distance between the rotational axis here and gravity is 0, so this is 0. Torque due to gravity is 0. This isn't the case when you take a plank and you don't put the pivot point at the middle, right? If we took a meter stick, for instance, right? Took anything and we tried to balance it and we put the pivot point, put the thing under at the fulcrum over here, obviously this is going to fall down this way. And that's because the gravity still acts on the center here. All right? Fg always acts on the center of mass of the object, center of gravity of the object. I'm going to use those two terms kind of interchangeably, center of mass, center of gravity. They are slightly different, but anyhow. To determine the torque due to gravity now, we just have to measure the distance between the force of gravity and the pivot point. So if we know this length total is 40 centimeters, all right, we know this is 10 centimeters here, this distance. Well, this also must be 10 centimeters then. So the torque due to gravity here is it's 0.1 kilograms, so that's 1 newton of force, times the distance to the axis, 10 centimeters, 0.1 meters. It's 0.1 newton meters is the net torque. And is it positive or negative? Well, in this case, it's technically negative because of the force trying to rotate it clockwise. All right, so for number 2, you're just going through and figuring out the net torque. For all of those setups, guys, you have to immediately draw the force of gravity in all of them. You can see this is the only one where the force of gravity is not going to apply a torque to try to rotate this thing. This one's a little hard to see. The pivot point is all the way on the left side of the plank. Number 3 is classic. Classic setup. Talk a little bit more about that. 0.3 kilogram sine. Determine the amount of tension the cable must be minimally be able to support. I'll make another video a little later on that maybe goes through one like number 3. It's very that's a classic one, right? At that point right there where the bar interacts with the wall, there's got to be something going on, right? So if it's fixed, so here we go. Let me just do basic setup of this one. All right, so there's 3 forces that are obviously acting. You got the force of gravity on this plank trying to rotate it. The pivot point, what is it? Well, here's a trick. You can actually put the pivot point anywhere, believe it or not, if it's static. You can actually pretend it's anywhere. And the torque, the reason you can do that is because since this is not rotating, it's in equilibrium, the torque about any point along this object, the net torque must be 0. If it wasn't, it would be spinning, right? So we usually just put the pivot point down on the left side for this problem, because then that eliminates any torque due to the wall, right? There's got to be some sort of force preventing this part from sliding up or down. It's usually friction or just some physical attachment force. And also, this cable is pulling it into the wall. So this one gets pretty complicated when you really start getting into it. But anyhow, force of gravity is pulling this down. The sign's pulling it down, force of the sign. And the tension, force of the cable, is also trying to rotate this plank, right? What's kind of interesting is when you do torque, you have to draw the forces at their point of application. That's something that comes up on the AP Physics exam, is draw the forces at their point of application. Well, literally that means where it is. This is a what's called a force diagram. A free body diagram doesn't work for rotational dynamics and torque. A free body diagram is when you represent the object with a point. And if we do that, it looks a little different. We have the cable, we have the gravity, we have the sign. All right. What else do we have? We have the wall supporting it this way, Fn, and there must be some sort of force of the wall holding it up, preventing that from sliding down. Now, what's interesting about this is in equilibrium too. These forces all have to be in equilibrium as well as for dynamic. If this isn't in equilibrium, then we have translational motion. This whole thing's either moving up or down or left or right. So we got to have that equilibrium and rotational equilibrium, which we have to look at the torque. So not only does the F net have to be 0, but also torque net must be 0, which is interesting. We don't really need that yet. You can hear my daughter yelling upstairs. Maybe you can. Yeah. Determine the amount of tension that the cable must minimally be able to support. So you're looking for the force of the cable that's got to make torque net equal to 0. See what you can do with that. You do have to do a little geometry here. We've got 1 meter here, 1 meter high. This is 3 meters long, so you can get the angle using tangent. All right. Anyhow, see what you can do with these. I hope that was a good enough introduction. Got a little long-winded there, but take a look at it. Ask me any questions. I'll talk to you guys later. Bye.